All right. Good afternoon. My name is Shashank Watadka. I apologize for not being able to present this in person, but I was unable to travel due to visa issues. This work that I'm going to present was jointly done with Aslan Chamkertin and has been submitted to ISIT. This talk is basically about local decoding and update of compressed data. And we're mainly the problem that we're interested in is efficiently storing and handling large, massive volumes of data. So we want to efficiently store large biological data sets. We typically do this by storing them on the cloud by using services such as Google Cloud and Amazon Web Services. However, however, this costs money, and the cost in terms of energy and money comes from so there are two main sources of costs. One is the storage itself, and the other is manipulation. So Google Cloud charges you for every gigabit of data that you store on their disks, and they also charge you for every single manipulation. So every time you download a file, or you copy a certain file, or you manipulate files on their database, you have to pay them money. So the goal, therefore, so want to design a scheme that lets you store huge volumes of data on the cloud, such that you can retrieve and update files as efficiently as possible. Now, in order to minimize storage, the solution that comes to mind is data compression. Basically, you can compress your entire data set and store it on the cloud. However, this is inefficient when you want to retrieve and update. If you compress your entire data using lempels, every time you want to modify, if every time you want to retrieve or update even a single file, you have to decompress and recompress the entire database. So this is clearly inefficient. The other solution would be to compress. You don't retrieval update is extremely efficient. You only retrieve what you need, and you update just what is required. However, this requires more storage. So the goal, therefore, is to design a compression scheme which has optimal rate, so you don't pay much for storage. At the same time, you want scheme practical, so the overall encoding and decoding complexity is as small as possible. At the same time, you want to be efficient in terms of the number of bits downloaded to recover a file and the number of bits uploaded in order to update a file. So basically, you want to minimize the number of bits of compressed data that you need to probe in order to recover a single message bit. And at the same time, you want to minimize the number of bits of compressed data that you need to modify in order to update a single message bit. So let me define this a little more formally. Suppose we have an n sequence, x1, x2 up till x, where each xi is drawn from some finite alphabet script x, and each entry is drawn independently and identically from some distributed x. Now, given any compression scheme that so a compression scheme would output an nr length binary sequence. So this is going to be the code word. The goal of local decoding is to cover individual symbols x1, x2, until xi as efficiently as possible. In other words, a local decoder is an algorithm which takes as input I between 1 and n, and with this as input, it probes a very small number of bits, outputs xi. The number of bits probed, which we will denote q of ixn, is something that will depend on I and also on the truth, and can depend on the source xn. And the goal is to minimize this number, the number of bits probed as much as possible. So the way we measure the efficiency, the local decodability, or the way we measure the efficiency of any compression algorithm through this quantity that we will term the average local decodability of the compression algorithm. So QD defined as the maximum over I of the average number of bits that is needed to recover xi, where this average is taken over the distribution of the source. On similar lines, we define local updatability or the update efficiency. So first, we need to define a model. So suppose we have an end sequence x1 through xn. When you compress this, you get a code word. Now suppose we update the ith file. In other words, the ith symbol is replaced with a new symbol xi tilde. Now the compression, now this when compressed gives new code word. The model that we use for updates is the following. So if we an I, which file to update, we replace xi, the new symbol xi tilde, which is independent, which is statistically independent of all the other symbols, and also it is distributed according to px. So in other words, xi tilde is allowed to depend on xi, but it's independent of all other xj's for j not equal to I. And at the same time, xi tilde still respects the statistics of the source. So both the old message and the new message are independent, have components which are independent and identically distributed according to px. So updating with this new symbol xi is bound to cause some changes in the new code word, and we want to do a compression scheme which ensures that the number that need to be made in the new code word is as small as possible. Now, in a practical scenario, the update algorithm will not have access to the entire code word or the entire message source. When you're working with a particular file, you know the location of the file in the database, but you don't have a local copy of the entire database itself. That would be extremely inefficient. Therefore, we want to design an algorithm for updates which is oblivious to xn or the true code word CNR. The only thing that the algorithm is given is the location of the symbol, perhaps the old symbol and the new symbol. So in other words, the update algorithm takes input I and xi tilde and possibly xi. Using this, it can choose to probe a small number of code word bits. So in order to object I, it probes some code word bits, and based on the code word, based on the values of the locations that have been probed, it decides it updates the it modifies the code word to the new code word, and we want to minimize the total number of bits that are probed and modified in order to handle the update of xi. So suppose that utot is the total number of bits and modified in order to update just xi with xi tilde. They measure the efficiency of a data compression algorithm using this parameter QU we call the update efficiency. So QU is the maximum over I of the average number of bits required to update xi with xi. Once again, the average is taken over the underlying source xn and the distribution of the new source xi tilde. Main contribution of this work is the following. We design an explicit compression scheme which achieves a rate close to the entropy of the. So the entropy is equal to so the rate equal to the entropy plus some small constant epsilon. This achieves a QD pair, which are constants independent of n, but these constants can depend on epsilon. The overall computational complexity of encoding and decoding is quasi-linear in. So in the rest of this talk, I will be focusing on the following. First, I'll give a naive solution to the problem of efficient local decoding and updates. Then I'll briefly describe what is known in the literature, and finally give a brief description of our solution. So the most obvious solution one could think of is to compress batches of files. So essentially, you take your n-length sequence, you partition the symbols in blocks of b symbols each, and you use a fixed length compression scheme to compress each block. So if you use an optimal compression scheme, then for a memoryless source, you could easily, so each block could be compressed using up to rate close to the entropy. But we want a fixed compression source such that the probability of vanishing probability of error means that we know that for any compression scheme, we require the size of the block B to grow at least as fast as order log n. So in other words, and for such a scheme, the number of bits that are needed in order to recover a single symbol or update a single symbol is equal to B, and therefore achieve QDQ equal to order log n. Now you may wonder that, okay, perhaps order log n is not so bad after all. After all, order log n is much smaller than log n, much smaller than n. However, there's an issue with this in the sense that if you want the probability of error to be vanishingly small, then every block must be typical, so that the concentration arguments go through. However, if you want let B to be typical, then really large. So in other words, order log n must be extremely large. So this is a very asymptotic result that you obtain. So what is known in the literature? Problems of a similar nature have been studied both in the computer science and the information theory community. Computer science community, problems of this field go by the name succinct data structures and probe models and so on. So these are problems that have been very well studied in the computer science community. However, these are all long-standing open problems, and it is not even known if you can design compression schemes which achieve the empirical entropy source. On the other hand, IT community, we know that better compression rates are possible. There are schemes which achieve schemes for memoryless sources which achieve rates close to the entropy of the source, and they can achieve local decodability of Q, which is a constant independent of n. These have also been extended to universal sources, and for universal compression and to sources with memory. However, it is also known that if you want to design a compression scheme with however, if you want to restrict your encoders to be linear in order to simplify encoder design, then you can't do any better than order log n. So in other words, if you want to design a locally decodable compression scheme, then the best QD that you can achieve is order log n. So any scheme that achieves QD less than log n must necessarily have nonlinear encoders and decoders. Now, to the best of our knowledge, only local decoding has been studied in the information theory community, and local updating has not really been even modeled. Another challenge of the schemes of Mazumdar and Tatwavadi is that these instructions are not explicit, and the encoders and decoders need not be polynomial time. So in the rest of this talk, I'm going to give a brief description of our compression scheme. So the main result, our main result is the following. So we have an explicit compression scheme, which for memoryless sources can achieve rates close to the entropy. The probability of error is decays faster than polynomial in n, but is not as fast as exponential. The local decodability and update efficiency that we achieve are both constants which depend on epsilon, but is independent of the block length n. The overall encoding and decoding complexity grows quasi-linearly in n, and our scheme is universal over memoryless sources. So in other words, the local the decode, the local encoder, the local decoder need not know the twist. So as a starting point for compression scheme, to gain some intuition, let us go back to the naive scheme that we discussed earlier. So basically, you look at the n-length sequence, you partition this into blocks of size b each. If b is any smaller than order log n, then we know that we cannot guarantee a single probability of error. Basically, compression scheme can guarantee a small probability of error. And the main reason is because if the size of each block is too small, then you don't have solution. But even if but suppose we look at blocks of size which are equal to a constant independent of n, then some of these blocks are going to be typical, but there is a large fraction of blocks which is going to be atypical. However, even if we look at any atypical block, we can all it turns out that we can always find a neighborhood. So basically, given this block, you can find a neighborhood of symbols or a neighborhood of blocks. So you basically expand the block till this chunk becomes typical. So you start with a small block, you slowly grow the size of this block, and you keep growing till you hit a point where the sequence is now typical. So for every block, you can find such a smallest neighborhood, which is typical, and the neighborhood for each block is going to be different. The size of the neighborhood is also going to be different. So at a very high level, our approach to obtaining efficient local decoding and efficient local updating is to encode information about the smallest typical neighborhood of each block. Now, it's not trivial to do this, and one needs to be a little intelligent in designing such a scheme which encodes such information. And what we have is essentially a multi-level compression scheme which achieves a small QE. So the scheme operates in level. At level 0, we partition the message symbols into chunks of constant size. So this and and corresponding to each chunk, we will generate a level 0 code word. So the level 0 code, and for the purposes of this talk, let us assume that we will use typical set compression. So given each block, generate a code word. If this block is typical, then the level 0 code word is equal to the index of this sequence in the typical set. If the sequence is atypical, then we store a 0 code to indicate that this sequence is atypical. If the sequence is typical, then we modify the original message. We place a marker at these places, indicate these parts have already been encoded, and the higher levels need not recompress these sequences. So to repeat, you partition the original message into blocks of very small sizes. corresponding to each block, you generate a code, a level 0 code word. If the sequence is, if this block is typical, then you store a non-zero code word, which corresponds to the index in the typical set. If this block is atypical, then you store a zero code word to indicate that the sequence was atypical. If this block is typical, if this block is atypical, then you do nothing to the original message. If this block is atypical, if this block is typical, then you place a marker in these blocks to indicate to the next level of the encoder that these parts have already been encoded and are not to be considered any further. So at level 1, we look at larger neighborhoods. So essentially, you group together blocks of you group together blocks from the previous level and generate blocks. So for example, in this case, this block has been obtained. So every block is obtained by grouping together 2 blocks of the method. And then you basically repeat the same procedure. If this block is typical, then if this is atypical, then you store a zero code word. If this is typical, then you place a marker for this entire block, entire super block, to indicate that this has been compressed, and this is atypical thing. And then this proceeds. So this is the basic compression scheme. And using these level 0, level 1, and level 2 code words to encode information about you essentially store multi-resolution information. So you store the information about the sequence at different resolutions. What is ultimately stored on disk is simply the continuation of the level 0, level 1, and level 2 code words. Now, how do we do decoding on this sequence? Suppose we want to recover this block. What we do is we first read the level 0 code word, check whether this is 0 or non-zero. If it is non-zero, then it means that this block is typical. This block is typical. If it is 0, then it means that this is atypical. So, for example, if you want to recover this block, then we read the 0 code word. This is non-zero, and therefore this must have been typical, and you can recover this just by looking at the typical set corresponding to the index stored here. Now, suppose we want to recover a symbol lies in this block, then we read the level 0 code word. Is this typical or atypical? This is this 0 or non-zero? 0, which means that this block must be typical. So we now look at a larger neighborhood. We go to level 1. Now look at the level code word. Is this 0 or non-zero? This is 0. Therefore, even the level 1 blocks, the large blocks, are also atypical. Now you look at the level. Now you look at level 2 code word. Is this 0 or non-zero? This is non-zero, and therefore we can recover this entire. We can obtain information about this entire neighborhood, and ultimately recover the symbol that we were basically interested in. Now, an interesting point here is that in this case, we can not only recover this symbol. So since we've looked at a sufficiently large neighborhood, we can essentially recover everything in this entire neighborhood. So by probing all the way up to level 2, we can recover not just this symbol which we were interested in, but also a much bigger sequence. So basically, we can reconstruct all of these symbols by going up level. By going to level 1, we can reconstruct these 2 symbols. So So the question is, how do we actually obtain uh, constant QD and constant QU? And the main intuition as to why we can obtain constant QD and QU is that once as you look at larger size blocks, the probability that a large block is typical is atypical is exponentially small in the size of the block. So as you look at larger neighborhoods, the probability that this particular neighborhood is atypical is overwhelmingly small. So in other words, you don't need to probe very high level. So in order to cover any particular symbol, you don't need to probe levels which are extremely high. So with a significant probability, it is sufficient to look at level 0 onwards. As you go to level 1, the probability that you will not be able to recover this symbol by probing up to level 1 is small. And this goes on. So a similar analysis can be done for local updatability. So to conclude, we gave a compression scheme. We studied the problem of simultaneous local encodability and update efficiency. And we designed a scheme that achieves constant local decodability and update efficiency on average. However, an interesting open problem is to design a scheme that achieves worst case constant local decodability and update efficiency. For more details about our work, you can take a look at our paper at our ISIT submission. The preprint is up on my website. Thank you.